Happy New Year, everybody. Alright. I mean, I'm in New York. Technically, it's a little bit early. There's still like 2, 3 hours for the actual New Year's, but still, it's the dot that counts. And either way, probably you are actually having a Happy New Year. So hope everyone's okay. This is day one of the year of January. Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me in Discord, and let's do problems together this year. There's also the weekly problem, which I would do afterwards. So but that'll be in another video, I guess. Anyway, let's get to it. 455, assign cookies. This is an easy one to start off the year. Assume you are... What? What? What is this first sentence? But that's pretty... I don't know. It's nice. Assume you are an awesome parent and want to give your children some cookies, but you should give each child at most one cookie. Each child I has a greed factor G sub I, which is the minimum size of a cookie that the child will be content with. And each cookie J has size S sub J. If S sub J is equal to G sub J, we can assign the cookie to your goal is the maximum. So it's kind of a sort of a matching problem, but of course this one is a very a standard one to a degree where it is just greedy, right? And you can kind of prove greedy by, in this particular problem, with the exchange argument. I keep on saying exchange argument. I don't know if I'm using it quite correctly, but the idea is that, let's say, you use greedy, right? And I know that this is easy, and in a way it is easy only because your intuition is greedy, and your intuition in this case is correct. I think the number one, maybe number two, top two say, question that I always get asked, and to be honest, this is something that I struggle with as well, is how do you know the greedy solution is correct, right? And yeah, when it's correct, it's easy. But if it's not, you're like, well, that was not right. And of course, in some other problems, there are multiple dimensions to be greedy on, and even with a greedy solution, it might not be the way that you think greedy would work. Anyway, so this is where proofs are helpful, and proofs are not always easy for greedy problems in general. There is like this, you have to prove the sub-Metroid thing, and greediness, and not a subproblem. I've been doing too many dynamic programming problems, but just like a smaller incremental state built to I think the way that they always say it's just like local optima built to global optima, right? So but that's like a very specific thing. Anyway, the way that at least I gone over a little bit to begin with is this idea of an exchange argument, right? And to say the exchange argument is kind of easy to remember because it is just in the name. So basically the idea is that, okay, so let's say you sort and you greedily give everyone the next biggest cookie that can fit, right? So in this case you have 3, 2, 1, and you have 1, 1. Let's say I sorted reverse order, right? For which one is, so G is the children? Okay, yeah. Right. And then the idea here is that this is not a great example, but let's change the bottom to say 2, 1, right? So one possible matching, of course, is just this 2, 1, and this is example 2. So, but also it's just very intuitive or easy to see why this is the optimal pairing, right? And the exchange argument is basically saying that if we exchange this, if you exchange in general any two elements or something like this. I mean, the actual details depend on the problem, but for this particular problem, if you change 2 elements, you can only get to a worst case, and you could it kind of is this thing that builds what is that called? Man, I don't remember anything today or this year. Well, I guess depending on what year, but induction is what I was going to say. But yeah, if you could show that it doesn't work in this case, then you can, or if you show that the exchange argument that you cannot exchange, then then in this way you can use induction to kind of prove the rest, kind of, right? Of course, in a lot of these cases, the exchange argument is going to be the way that I do it anyway. There are probably smarter, more mathematical way of doing it, but the way that I do it is just really exhaustive. And this is for any given, let's say xy, or maybe a, b, and then s is just some c and d in a more general case. And let's say that in this case a is greater than c, a is greater than b, a is greater than c, it has to, or equal to, it has to for it to match, of course, and b is greater than or equal to d. Then in this case, let's say you exchanged it to AB, DC, right? Then in this case, of course, oh, I missed a thing where C is greater than or equal to D, right? Because let's just say that we have it, right? Well, in this case, well, now you can kind of think about all the possible scenarios, right? So one scenario is that A is greater than or equal to D, right? Let me just label this as scenario 1. And B is greater than or equal to C. And the other things don't really matter. You have 2 matches, right? And then the scenario 2 is similar, but you have, because D is smaller than C, right? So this thing is still true. Then now A will always be greater than or equal to D in this case. But there's a chance where B is not, I don't know if that's quite the emoji for it, but you get the idea, right? B is actually less than C, just due to how, and you could plug in real numbers. So there's 2 scenarios. In this case, there's 1 match. So now you're going from 2 guaranteed 2 matches. I guess maybe it's here actually, sorry. 2 matches to either same optimality or even worse. So therefore, by the exchange argument, you always want the greedy solution. That's kind of the idea about it. I mean, you can actually do this a little bit more rigorously, but that's basically the template for me anyway, of like, oh, okay, so this is why greedy works. The other thing is that, and for this particular case, it is just that, it just proves that if you have something that strays from this, and of course, if you sort everything in a reverse order, my mouse is a little bit weird. Sorry, hang on. Maybe my keypad, my mouse pad's a little weird. But yeah, you can show that if you sort this, then this will always be true for another, like maybe I should have used different variable names, but yeah, for more variables on G or S, you can kind of prove this in you could do it for every pair, and of course, all the things look the same, and therefore you can prove that this is, optimal just by almost exhaustion, I guess. I'm always exhausted. Anyway, that's basically the idea. That's a very long way. I just want to kind of give you the tools a little bit. I mean, I don't think this, like I said, this is a quote-unquote easy, and a lot of you probably already know how to do it. I wouldn't be surprised. So the code is actually not that interesting, I don't think, maybe. And then now, count is equal to 0, right? Or cookies is equal to 0, maybe? I don't know. So now for, maybe, okay. So this is kind of like the, the 2-finger algorithm. So maybe I'll have gi is equal to si is equal to 0. While gi is less than length of g, and si is length of s, and you need both of these to be, to have an item. Then now, so now, so the other thing about this is that the beauty is that, I guess this is kind of part of the proof as well, is that if you have a G that is bigger than the biggest S, the biggest G is bigger than the biggest S, and by definition, no cookie is going to fit that person anyway, right? Because if you can already consume the biggest cookie, then, or if there's no cookies for it to consume, yeah. the size of the cookie. I guess that's what I was looking for. Okay, fine. Right, so basically, if g of gi is greater than s of si, then what happens? That means that no cookie for gi, so then we do gi increment by 1, and then we continue. Otherwise, then now this means that g of gi is, so that means that this cookie is good, so then we eat the cookie, oops, and increment, and that's pretty much it. I mean, this is, which I get a mistake, 1371 day streak. But yeah, I mean, like I said, this code and even this idea is not very hard, but you know, I just want to give you a little bit of a basis, a little bit of a template for the code. All right, this is going to be n log n time, of course, because of the sorting. Yeah, if you want to be more precise, where g is, the length of g is n, the length of s is m, then you have n log n plus m log m. You can also maybe bound that a little bit if you like. For example, you can maybe even bound that by like n log m or something like this, using a heap, depending on what n and m is, but I'm not going to, and the other way around as well. But in a simple case, in this particular code, let's just say there's going to be n log n plus m log m. And of course, this is going to be n plus m space, because the sorting does require extra space. I mean, the way I wrote it is, you know, whatever. But anyway, that's all I have for this one. Happy New Year, everybody. Let's do this year together. I don't know if I'm going to do the entire year, but I'm going to do at least for a little bit. So we'll see how long the streak ends up going. Mental health. I'll see y'all later and take care. Bye-bye.